So the sharp point is facing you. The sharp point is facing you, and then you overlay them to the best of your ability. Okay, there we go. You are now two guys lying together like this. Now, because you are going to be rotating this thing, moving it, that's why you rotate. In order to make sure that, guys, don't get lost in your own personal discussions. Are you winning there? However, the sharp point pointing towards you, and then the forge head at the bottom. You know, you should be able to rotate this thing freely, like the tracing paper on top. Now, so that you don't lose a sense of where you come from. Alright, on the tracing paper, you just mark your north line there. Make sure that it is in line with that, and then your south line there, which is 180, and then your east line, of course, is 270, and then you go there 90. All right. Now we start with the joint. The joint is dipping 60 degrees. Okay? But you don't start with a dip. You start first with its direction. Okay? So this stuff is the dip direction. What is that? 80. So 80 is a point somewhere there. I'm going to use green for the joint. There's a point there. Right. Now you need to measure, you need to plot its dip. Right. The dip can only be measured along the horizontal, the midpoint horizontal line. It means now you have to move that point to a 90-degree line. If it had plotted there, you can take it all the way to the 90-degree line if you want, but you don't have to. You can make it align with the 270. If this thing had plotted there. So in other words, what I'm saying is, even if I were to do that, it will still be the same. Right? Remember, your dip is your 90-degree 279. So you move this point of your joint A, your joint there. When you are there now, along this line, you measure the dip. Each one of these that black big lines represent 10 degrees. So your dip of that thing is 60 degrees. It means 10, 20, 30, 40, 50, 60. There on that line, you plot the great circle. You must listen to the names that I'm using here. You plot the great circle of your joint. You know, it's always good to say the great circle of your joint, and just put the J so that you remember what that is. And then you return this thing to the alignment on your north and your south. And that will be aligned. You got your great circle of your joint. Now you plot the fold. The fold is 200 and what? What is it? 250. Okay, 250. This 180. This is 270. This is 260. Therefore, 250 is here. 60, 70, 250 is there. Right? So you move it to a deep line. A deep line is your midpoint, 90, 270. Great circle is a line. Right? Then you measure that dip, which is what, 50? 10, 20, 30, 40, 50. Okay? So on that, what is that? Is your fault. Am I right? The great circle of your fault. Then you will turn this thing. Now, you already have some information now as far as this thing is concerned. What we have what we call a line of intersection of your joint and your fault. Your fault and your joint, they will meet somewhere. You know, this is your fault, this is your joint. They will meet somewhere. Alright? And then where they meet, this line there, remember they won't meet at the point. These are not rods, they are planes. So they will meet, there will be a line where they will meet. A line of intersection where they meet, will be meeting any other house. Now that line of intersection is this. The blue line. The blue line here. Passing right through there. Right? You just do that. The line of intersection. Okay? Of intersection, which is nothing else but what? The direction of sliding. It means, what does it mean? It means if these two guys will form a wedge with a slope face, the direction of sliding, that wedge will slide along this direction, will slide something southward, in a southward direction. If you know, other than, you can't see southward, of course, there is something like what? This is 180, this is 170, this is 172, 170, 170, what 168, 168, that will be the direction of sliding of that wedge. Okay? But we really haven't confirmed that wedge yet. All we know is that our joint and our fault are intersecting. Okay? And then they define a line of intersection. If a wedge was to form with a slope face, it will slide along that direction. So far we know that. Right. Now, while we're still there, there is also what we call the pole of a great circle. Right? The pole of a great circle, instead of a whole circle, you can represent a great circle with a point, a single point. Right? Especially if you got a lot of joints. You cannot do this for every. If you got 30 joints and you want to represent them here, it's going to be a mess. But you can represent them with the poles. And when the poles are closer together, they tell you of one thing, they tell you that your joints are more or less similar. They're more or less similar joints. Right? But we'll leave that for now. Now, let us plot the pole of the joint. Okay? To plot the pole of the joint, you go to that great circle of your joint. See? That's your great circle of your joint. The one that is passing right there and right there. Just like, that means in line with that thing. And then the pole is 90 degrees from here to the other side. So 10, 20, 30, 40, 50, 60, 70, 80, 90. So here you've got the pole of the joint. Yeah. Right. Let us plot the pole of the fault. Okay. You know, it is better to really listen rather than to try to, you know, rather than to try to it's good to follow, but do not get lost in the while I'm still talking. Alright? And then what you do now, you're looking for the pole of your fault. You come there, and there's a 10, here is it. You put it in a great circle. Right? It must fall in line with one of these great circles. These are called the great circles, and this along this line are deep lines. So it's 10, 20, 30, 40, 50, 60, 70, 80, 90. So here we got the pole of the fault. Now, this is the magic. Now you have to try to get these two poles to fall in one great circle. So you just look for that magical position. Magical position. Any 2 points must find home there. So see, so there it is really. So this now is going to be the great circle of the poles of your joint and your fault. So you bring it down. Bring it down. Let's say it comes. You know, it cannot be very, very accurate, but it get to be there. You understand what I'm saying? As accurate as you can. You know, you cannot be out by 100 degrees. You know, 20. It means you didn't do something that's right. Alright. Now what is this? This is the great circle. This is the great circle of your joint and your fault poles. Great circle of the poles. Right. Now, something is very interesting about this. Can you tell what it is? Now, the pole of that great circle of the poles, right, is plotting here. Exactly. So it means you can either use the poles method to find your direction of sliding or your line of intersection without using the great circles. Because if you can just plot these two and find their poles and find the pole of that great circle. The pole of what is the pole of this great circle? The pole of this great circle is counting from here 10, 20, 30, 40, 50, 60, 70, 80, 90. It comes there. It coincides perfectly with that line. So a straight line, therefore, through the center of that great circle will also define the line of intersection in the direction of sliding. So I've arrived at the direction of sliding or line of intersection using two methods. Using a point where your joint intersect your fault and a straight line through there. So line of intersection in the direction of sliding. Or you plot the poles of the two joints, the joint and the fault, and the pole of that great circle will also give you that. So, you can be asked to, there's many ways to arrive there. Now, that is what we have. Now, we have to now plot the slope face so that we can see really where is our wedge really going to be. What is the slope face? It's 80 degrees and it's striking 130. Is that right? So we bring this thing to normal to align well, and then you like what? This is 90, 100, 110, 120, So the dip, so this is the slope face. This is the slope face. This is a fault. This point here is for the fault. And I think this one is the joint. Okay. Right. Now 80 is of course just 10 degrees from 90. So your slope face. This is your slope face. This is your slope face. The great circle of your slope face. Bring this stuff here. Alright. What have we got here? We've got interesting points here. This is the blue guy. Defining your wedge. Remember, this is your direction of flight. So now, this will be now your wedge, you know. This stuff here is your wedge. Your slope face and the joint and the fault, they come together in a magical way to form a wedge in the high wall. This wedge can come down, this wedge can fail. We don't know. We must find out. Not every wedge will fail. If you think about it, you can have a wedge that is deep inside. This is, you know, your joints come in, maybe your joints are sitting like that. They are dividing from the bottom like that, and then your line of intersection, or your direction of sliding is inside. While this is the slope face. So you have a wedge, but it will not slide out. Because this direction of sliding is into the solid. So, so far, we don't know what is this. So, we must now determine if this wedge will fail. Now, for that environment, let's say, for example, now, you have also been given that your friction angle, the general friction angle of your planes, theta, let's say 30 degrees. If you like. 30 degrees friction. You know, almost every plane, you know, every plane that can slide is got a friction. Now we have to plot that friction angle this way. Right. How do we plot the friction angle? All we know about the friction angle is that it is 35 degrees, 30 degrees. Nothing about this direction or this deep. Is there a deep of friction angle? Friction angle by itself is inherently describing the dip or the slope or the inclination at which the thing will fail. Okay? So now this is how we're going about plotting our friction angle. We plot it with a pencil. What we do, we align this thing, then we say 30 degrees, is that right? Say 10, 20, 30. Make a mark there. 10, 20, 30, you make a mark there. You rotate this thing a little bit. 10, 20, 30, you make a mark there. 10, 20, 30, you make a mark there. We are plotting the friction circle. 10, 20, 30, you make a mark there. Remember please, your dips are always measured along the 99 or the 270 centimeters. 10, 20, 30, you make a mark there. 10, 20, 30, you make your mark there. 10, 20, 30, and make your mark there. Guys, you must watch me carefully. If I make a mistake and block the day, it's going to be a mess. You know, you must help me out. I'm also human. It's just that I will not fail. You will. 10, 20, 30. 10, 20, 30. Make sure it's around the 90-degree line. 10, 20, 30. Okay, now you see this bloody thing is a circle. Can't you see that? So you just, you know, as best as you can. As best as you can, you do that. Now you have your friction circle. Let's go back there. Good. You got your friction circle. Now, I'll tell you one thing. If this pole plot inside this region between the slope face, if it plots inside this region, this pole point, you're more likely you're really now begin to, you know, to cut down on assumptions and things. You are now more likely that you will have this thing will likely fail. Okay, it will likely be unstable. This is. But now in this case, it's floating outside. See there? It's floating outside. It doesn't really mean, at this point, it doesn't mean that it will not fail. You know, it is likely that it will not fail. It is likely that it will be stable. Now, we have to further determine this thing. And now, the way to do it is to bring, you know, this is the direction of sliding. Okay? Bring the direction of sliding there. You bring it along the 90 degree. There's interesting angles we need to measure here that will make us determine the finality of this question. If this wedge will be stable or not. What you do, you bring your line. Now remember, if you need to measure angles, they are always going to be along that 90 to 79. So if you are measuring an angle of anything, and your reference is not aligned with that, the 90-degree line, then you are not measuring angles. You don't know what you're doing. You will be wrong. You will be incorrect. So that's not really wrong. It's not a sin. You will be incorrect. Alright, now the plunge, okay, the plunge or the dip of the line of intersection. Remember, you got a joint intersecting the fourth, right? Let's say they're doing something as funny as that, right? This line of intersection is a deep in a deep direction by itself. It's got a deep and a deep direction. We already know the deep direction of this thing. The deep direction, also known as the plunge, which is the plunge of that wedge is measured up to the hole, or up to the point of intersection. So now it means to measure that angle. This is what we have to do. Make sure that this stuff is perpendicular. Okay? Make sure that you draw a perpendicular line from there. You use the grid circle, you use this. Alright. There. Okay, so you got an angle there. Does anybody know the sign of this thing? What is it called? Huh? It's a Greek letter. Simple. What is it? Huh? Come again. The friction angle, what is that? What is this? What is this? What is it?
Sigma.
Huh? No. Sigma is this. What is this? Phi. That's right. And then what is it? What is this?
Omega.
Huh? Come again?
Oh, yeah. Is it an omega or
No, psi. One is phi, the other one is psi. Okay. Learn to call things by the name. Alright. You got an angle there. What is its magnitude? It's about 10, is that right?
yes?
About 10, eh? About 10. The deep, you got to 10, about 10. 10 degrees. Alright. Good. And we have to compare it with the depth of the line of the slope face along the line of intersection. Along the line of this is a line of intersection. So it means you are going to measure your stuff all the way there. Right? So your line of intersection of direction of sliding, it meets up with your slope face there. You see that? You see that? You must be seeing it. I'm showing you that. Now, here is another angle of our interest. Okay? Which is the dip of the slope face along the line of intersection, or along the direction of sliding, which is psi f, the slope face. Okay, now failure is possible. Okay? Failure is possible if, of course, that angle, what is it? Let's measure it. Let's measure it. What is it?
79.
Something like, that is 80, that is 78, more or less 78. 78 degrees. if that is greater than that, failure is possible. It is possible that this thing can fail. Right? But failure now can't be guaranteed that this thing will fail. You must differentiate between the two. This thing can fail, and this thing will fail. When will it fail? Now it's possible. When will it fail? It will fail if, of course, this is still met. And that is greater than 5. All right. But that is not the case. What we have is that that is that, that is that. Okay, guys, you must talk when I'm outside the jurisdiction, so that we can see. That is there, that is met, but it is, okay, this is less than 5. 5 is bigger than your plunge. Okay, your friction angle is bigger than your plunge. So failure is not guaranteed. Failure remains possible. If now, for example, water starts to come in, right? Water starts to rain, water starts to come in, and it starts to run through the joints and the faults, and it delineates the strength of your joints. It means increasing, or it means actually decreasing your friction angle. All of a sudden, your friction angle becomes so low because all of a sudden that stuff is wet. It slides easily, right? So it means now your friction angle is going to be somewhere there. Let's say it starts to rain and your friction angle decreases from 30 to 5 degrees, and it comes and it plots there. So you've got now a new friction angle plotting there, plotting outside this thing, right? So it will mean that, let's say now your friction angle is 5 degrees Celsius. So now you will have an instance whereby you have that. In this instance, we can say without doubt that this stuff will fail. This stuff will slide. That is how the stereonets are used for that purpose. There is a reason why rain is #1 enemy for your open pits and open cast for this particular reason. It starts to rain, water starts to find itself a path through the joints, through the faults, through all these discontinuities, and it lessens the frictional properties of this thing. It weakens the cohesion, the strength of the plane. All of a sudden, your friction angle becomes less and less and less, and then you have failure. That is the reason why you have to what? Drain your stool face. If you've got a lot of joints in your environment, you just drill holes into that thing, especially the bottom, so that water don't get to stay inside. Because when the water starts to stay inside that thing, we're moving now to another issue. You know, this is your high walls, this is your joints. You just drill the drainage holes. Alright? It means even if water comes through here, it do damage. It doesn't get to be locked in and create what? High pressure. So you can drain your scoops. No, as long as you don't contain water. Now, if you have a wedge, now we're going back to something that is very much related. Yes. That's better.